go as a set of ordered pairs in which every number in the domain corresponds to exactly one number in the range. Want to review that, but actually want to back up one step in front of that. Before we defined a function, we defined a relation. Said a relation was any set of ordered pairs at all. And so, for example, the relation that we see right here, relation A, I'll go ahead and copy all three of these. Relation A, we could look at it and ask ourselves whether or not relation A is a function. What do you think? Got a 4 and a 5 and a 7 in the domain, and 9, 11, 13, and 15 in the range. And for relation A, 4 corresponds to 9, 5 corresponds to 11, 4 corresponds to 13, and 7 corresponds to 15. Is this a function?
Yes.
No.
I want to say maybe not. Why might this not be a function?
It's the 4.
The number 4 corresponds, the number 4 corresponds to, that is really not good, to two different numbers in the range. Okay, 4 corresponds to 9, and 4 also corresponds to 13. So that's enough to disqualify this from being a function. How about relation B? Let's see if this is a function. Relation B. We've got a domain and a range. There's a 4 and a 5 and a 6 and a 7. In the range, there's a 9, 11, and 13. So 4 corresponds to 9, 5 corresponds to 11, 6 corresponds to 13, 7 corresponds to 9. Is this a function? It is. So A was not a function. Relation B, this is a function. But the fact that the 4 and the 7 both correspond to that 9 caused this to be, it causes this to be not as nice a function as we're going to need it to be in this section on inverses of functions. Want to define, before we look at example C, want to define the inverse relation of a relation B. We're going to call it B inverse. I'll write it with a superscript of -1. The way we form the inverse relation is we take a relation, usually we start with a function, B is a function, and just interchange all the x's and y's. Take the 4, 9 and change that to 9, 4. Take the 5, 11 and change that to 11, 5. Take the 6, 13 and change that to 13, 6. And take the 7, 9 and change that to 9, 7. This is called the inverse relation of the function B. Now it may or may not be a function itself. What do you think? 9, 11, 13, 4, 5, 6, 7. 9 corresponds to 4, 11 corresponds to 5, 13 corresponds to 6, 9 corresponds to 7. Is this a function? No, it fails to be a function because of the 9. 9 corresponds both to the 4 and to the 7. That's a no-no if we want our relation to be a function. And it's due to the fact that for this function, B, the 7 and the 4 both corresponded to that 9. So for the number 9, it was 2 numbers in the domain corresponding to that 1 number in the range. If it had just been 1 number in the domain corresponding to every 1 number in the range, then it would have been okay. We could have interchanged the x's and y's, and after having done so, we would have gotten a function. So, inverse relation B inverse, this is not a function. In this case, now we want it to be. We want it to be a function. So consider, and I guess what I probably should have done, I don't think it'll let me cut, but I can copy. Let's copy example C here and see what this one looks like. Domain range. We've got 4, 5, 6, 7, 9, 11, 13, 15. 4 corresponds to 9, 5 corresponds to 11, 6 corresponds to 13, 7 corresponds to 15. Is this a function? Yes, it is. Every number in the domain has exactly one arrow going out of it. Now, so this relation C, this is a function. What if we interchange all the ordered pairs, the x's and y's of all the ordered pairs, and form the inverse relation C inverse? What we would have is 9, 11, 13, 15, 4, 5, 6, 7, and it basically reverses all of the arrows. Is C inverse a function? Yes. So if we have a function and we interchange the x's and y's of all the ordered pairs, and that too is a function, then what we have is a one-to-one function. Since this is a function, it means that relation C is a one-to-one function. The definition of one-to-one function ought to be given here down at the bottom of the page. A one-to-one function is a function in which each element in the range is corresponded to by exactly one element of the domain. And that's precisely what happens. The 9 is corresponded to only by the 4. The 11 is corresponded to only by the 5. The 13 is corresponded to only by the 6. And the 15 is corresponded to only by the 7. Every number in the range has exactly one arrow pointing at it. And so that makes this a one-to-one function. So it's got to be a function. Every x has to correspond to exactly one y. And then, in addition to that, if every y is corresponded to by exactly one x, it's going to be a one-to-one function. Now, remember the vertical line test. We could draw a vertical line. We can test the graph of a relation to see whether or not it's the graph of a function. Is this the graph of a function? It's not. It fails the vertical line test. We can draw a vertical line through this, like so, and intersect it in more than one point. If we consider the coordinates of those points, let's say this is a particular value of x, and this is y sub 1, and this is y sub 2. If we look at the ordered pairs, we've got x corresponding to y sub 1, and x also corresponding to y sub 2. If we do the little mapping diagram, x, y sub 1, y sub 2, single x pointing to more than one y, we can see it's not a function. So this is not a function. How about this? This a function? It is. It passes the vertical line test. We can draw vertical lines all up and down here. And it will be a function. Not a function that's going to have an inverse that's a function. Is it a one-to-one function? Not one-to-one because it fails the horizontal line test. And let's watch it fail. There we go. If we can intersect the graph in more than 1 point by any horizontal line, then it is not a one-to-one function. Because for most of the range of this function, it's two different x's corresponding to a particular y. Let's say we have y right there. That y is corresponded to by this x value here, and it's also corresponded to by this x value here. If we look at the points on the graph, that's x sub 1y, that's x sub 2y, and if we do a little partial mapping diagram, we've got x sub 1 and x sub 2 both pointing at the y. So for the major portion of the range of this function, it's 2 to 1, not 1 to 1. So it's a function, but not 1 to 1. So, what the graph of a 1 to 1 function look like? The most popular answer I usually get when I ask that question is, well, a straight line. Slanted. Not a vertical line, because that fails the vertical line test miserably and is not a function. Not a horizontal line, because that fails the horizontal line test miserably, and that's not a one-to-one function. It's infinity to 1. But a slanted line like this is going to pass the vertical line test. It's going to pass the horizontal line test, and that's going to be an example of a one-to-one function. It can have positive slope. It could have negative slope. That would be okay. Both those are going to pass the horizontal line test. Doesn't have to be a straight line, though. It could do something like that. A sufficient condition for a graph to be the graph, or let me say this, for a function to be a one-to-one function, is that it be either increasing on its entire domain or decreasing on its entire domain. If we draw the graph that does something like that, then that would pass the horizontal line test as well as the vertical line test. That would be one-to-one. Now, if you're willing to go with the piecewise function, piecewise defined function, you might get it to increase for a while up here and then decrease for a while down here. And somehow still, if it jumps in between, somehow still pass the horizontal line test. So it doesn't have to satisfy that property to be one-to-one. But if it's increasing on its entire domain or decreasing on its entire domain, that's enough to classify it as one-to-one. So these all are graphs of one-to-one functions. Y'all pass both the vertical line test and the horizontal line test. Now, example 1, I wish I'd provided these graphs. We can graph these functions on the calculator. Let's do so, and then use the horizontal line test to determine whether they are one-to-one or not. So first on the list, you really don't need to see the graph of this to know what it looks like. At least I hope you don't. F of x equals 2x minus 4. What does 2x minus 4 look like? Zoom 6. Zoom 6. Straight line with a slope of 2 and a y-intercept of negative 4. So for example 1, f of x equals 2x minus 4. There's the picture. And is it a one-to-one function? Yes. So we'll say yes, it's one-to-one. Passes the horizontal line test. Now all these are functions. What's the next one? F of x equals x squared minus 4x plus 3. Is this going to pass the horizontal line test? I'm thinking not. This is 2-to-1 for most of its range. So it's not 1-to-1. How about example 1C? And let's see if I can, so I have to copy it. Well, that would have been easy enough to change. X cubed minus 5x plus 3. X cubed minus 5x plus 3. Is that going to be 1 to 1? Yeah, I think it is. Oh.
No, is it, it's like a snake, so it comes back down, so it passes the vertical, but not the horizontal.
Oh, that's, I'm thinking of absolute. Never mind. Absolute.
This looks like it fails the horizontal line test. This is not a 1-to-1 function. For a significant portion of its range, from about negative 1 point something to positive 7 or 8 point something, it's actually 3 to 1. Any horizontal line in here is going to intersect in 3 points. So it's single y is corresponded to by 3 different x's along that range. So that's going to be a no. And what about the last one? X cubed minus 6x squared plus 13x minus 6.
Sorry.
The portion of the graph that we can see appears to pass the horizontal line test. Now, it's not to say that it might go outside of this viewing window and do something crazy, turn around and decrease, but it turns out that it doesn't. All it does is, as we look down below, it goes down, 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 like that, and up the other side, up, 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 up. This passes the horizontal line test, so this is a 1-to-1 function. So we'll put that there. This is a no. But this is a yes. So linear functions, as long as they're not constant, are going to be 1-to-1 functions. Quadratic functions, x squared term, we'll talk about quadratic functions ad nauseum in section 3.1. We have that to look forward to. But their graphs are going to be parabolas, either that open up or down. But as such, they're always going to fail the horizontal line test. So they're not going to be 1-to-1. Some third-degree polynomial functions are 1-to-1. Some other third-degree polynomial functions, whoops, this is one that is 1-to-1, I guess, and other third-degree polynomial functions are not 1-to-1. So some are and some aren't. You can't tell just by the degree unless it's first or second degree. Well, turns out if the degree is even.
So first degrees will always
First degree are always going to be 1-to-1. Even degree, it turns out, I have to be clear about this. Even degree, although I haven't given an example of a 4th degree or a 6th degree, even degree polynomial functions will always fail to be 1-to-1. If the degree is odd, sometimes it's 1-to-1, sometimes it's not. Definition of the inverse of a function. If we have a couple of functions that are defined using algebraic expressions rather than just a handful of ordered pairs, then we might want to explore the question, well, here's a function f, here's a function g. I wonder if these are inverses of each other or not. How would one tell such a thing? Well, what we do is we compose them with each other. Here's what we want to happen. Suppose we have the domain of g. And over here, we have the domain of f. We want a number x where we evaluate the function g at x just like that, and it sends us, we hope, it certainly sends us to the range of g, but we hope it sends us to the domain of f. When it does, there's g of x right there. What f does is it sends us right back so that f of g of x actually equals x. So that needs to happen for every x in the domain of G. And then, suppose we have an x in the domain of F. So pick an x right there. And over here, we've got the domain of G. Well, certainly, F is going to send us to the range of F, but we're hoping that's in the domain of G. So it sends us right there to f of x. And then what does the function g do to that? Well, it sends it right back. So that g of f of x equals x. So whatever the function f does to a function, whatever the function f does to a number in its domain, the inverse function undoes that. And it gives you back the number that you started with. That's the idea here. We also have this blurb from the reading quiz. The domain of the function f is equal to the range of its inverse. There's a role reversal. X's that start out in the domain of f, once we interchange the ordered pairs, they end up in the range of the inverse function. And y values that start out in the range of f, when we interchange the x's and y's, they end up as x's for the inverse function. Let's try this with a particular function f, particular function g. Do the composition both ways, f of g of x, g of f of x, and see if it doesn't give us x in both cases. So example 2. Show that g of x equals 1fx minus 3 is the inverse of the function f of x equals 2x plus 6. Now go ahead and state the domain and range of each of these functions. All real numbers. These are linear functions, non-constant linear functions, and they both have all real numbers in their domains and all real numbers in their ranges. It would be a little bit more interesting if there were some restrictions here and there, but there are none. So all real numbers all the way around. Let's just do the composition. F of g of x. So x has to be in the domain of g, but it just has to be a real number to be there. So we could pick an x any x. F of g of x equals f of 1/2 x minus 3.
Now that's where I got on the quiz.
Yes.
Because I was thinking back for the previous part where it was 3 1/3 reversing.
Right.
So here you have your 1/2 x. So when I was doing the quiz today and you had an option of the 1/3, how come I don't understand why that wouldn't have been 1/3?
Let's see. Oh, on the reading quiz.
You reversed it back to the regular 3 as opposed to.
Right.
I think I'm combining all my chapters now.
Right. Yeah. If we have f of 3 and it's 5 or whatever, then f inverse of that is going to give us back the original number. Because if f of 3 equals 5, then f inverse of 5 must equal 3. Sends us right back. So if we do this, then f of 3 would be 5, and f inverse of 5 would be 3. So that's kind of the idea. Function takes us somewhere, the inverse sends us right back. So for this particular function, f of 1/2 x minus 3, if we look at the function f is the function that first multiplies by 2 and then adds 6. So it multiplies by 2 and then adds 6. That's okay. So let's take the 1/2 x minus 3, multiply it by 2, and then add 6. So it's going to be 2 times 1/2 x minus 3. Then we'll add the 6. Distribute the 2 across the parentheses. 2 times 1/2 x equals x. 2 times negative 3 equals negative 6. And then we add the 6. The negative 6 and the 6 cancel. So it gives us x. So we needed this to be true. We also need the reverse to be true. We need g of f of x also to equal x. We'll check that in a minute. I need someone to give me an even number from 10 to 100.
22.
22 is an even number from 10 to 100. So what is g of 22? I said even because I want to take half of it and get a whole number. Half of 22 is 11. 11 minus 3 is 8. So g of 22 equals 8. Well, what is f of 8? 2 times 8 equals 16. 16 plus 6 is 22. So g takes the number 22 and sends it to 8. F takes the number 8 and basically tells where it came from. It came from the number 22. So whatever the function g does, the function f undoes. Well, let's see if g undoes the work of the function f. This is going to be g of 2x plus 6. So it's going to be, well, g is a function that first takes half of something and then subtracts 3. So it'd take half of the 2x plus 6. What's half of 2x plus 6? X plus 3. And then subtract 3 from that.
Now, why did you do minus 3? Because it was half of the original equation up there? Oh,
This minus 3 is from that minus 3 up there. Mm-hmm. So not necessarily an even number, but preferably a whole number. Is someone give me a whole number from 10 to 100? 10, okay. Let's go with 10. What is f of 10? 2 times 10 is 20. 20 plus 6 is 26. What is g of 26? Half of 26 is 13. 13 minus 3 equals 10. So f takes the 10, sends it to 26. G takes 26, sends it back to 10. So what the function f does, the function g undoes and gives us back what we started. These inverse functions are a useful feature in equation solving. Equation solving, you've got a lot of built-in arithmetic operations in an algebraic expression, and if we could have a function that would undo all that's done in the process of evaluating the algebraic expression, it could give us the solution x. So it's a useful thing to be able to have the inverse of some complicated algebraic expression. It kind of uncomplicates everything, and that's certainly a good thing. All right. I mean, it seemed like it at this point, but that's the goal. That's the goal. Graphs. There's a nice relationship between the graph of a one-to-one function and the graph of its inverse. To see what that is, let's look at the graph of f of x equals the square root of x minus 2. If we're going to plot some points to see what the graph of the square root of x minus 2 would look like, it would be helpful to know the domain, so we'd know what x values to choose. This does not have all real numbers in its domain. What is the least number in the domain of the square root of x minus 2? If we're going to take the square root of x minus 2, get a real number as the answer, x minus 2 better be greater than or equal to 0, so x itself better be greater than or equal to 2. So let's pick some nice numbers that are greater than or equal to 2 and use them to evaluate the function. So let's see, put some tick marks here. 1, 2, 3, 4, 5, 6. And I'm going to try to make it a square viewing window if I can. It's hard to do. I don't know if just make these. I don't have a square viewing window. Go at least that high. Pretty close. What is f of 2? It's 0. 2 minus 2 equals 0, and the square root of 0 is 0. So we put the point 2, 0 right there. What is f of 3? It's 1. 3 minus 2 is 1. The square root of 1 is 1. So let's plot the point 2, 1. And we could find f of 3, we could find f of 4. They're irrational, but we could plot points if we wanted to. Just have to round them off a little bit.
So that's 2-1 or 3-1?
It's 3-1, thank you.
Yeah.
I was trying to think ahead of myself, and I didn't think where I was. That's 3-1, thanks. Let's try f of 6. What is f of 6? F of 6, 6 minus 2 is 4. Square root of 4 is 2. So that's the point 6, 2. That's really important that I label these points correctly. Because to form the inverse... Good, I didn't really like that graph anyway. To form... and I really don't like that one. One more try. Good enough. To form the inverse, it's like forming the inverse relation of a function. We interchange the x's and y's of all the ordered pairs. So if the point 2, 0 is on the graph of this function... Oh, forgot to ask. Is it 1-to-1?
Yeah.
Passes the horizontal line test. Yes, it does. It's an increasing function. In fact, it's a transformation of the square root function. You see, the graph of the square root function would look something like this, and we've taken the graph of the square root function and shifted it 2 units which way? To the right, and that makes sense because we substitute x minus 2 for x. That's the operation that shifts 2 units to the right. Sorry, I didn't mean to bring back unhappy memories of that section. If the point 2, 0 is on the graph of this 1-to-1 function, what point then is on the graph of its inverse? 0, 2. So right there, that is a point on the graph of the inverse. 3, 1 is on this graph. What point's on the graph of the inverse?
1, 3.
1, 3. And 6, 2 is on this graph. So the point 2, 6 is on the graph of the inverse. Now the size and shape of the graph of the inverse function will always be the same as the size and shape of the graph of the original 1-to-1 function, just it's going to be oriented differently in the plane. It's going to be the result of a reflection, but not a traditional reflection that we've studied so far, not one of the types that we've studied so far. So let's see. I'm going to try to sketch the graph of half of a parabola. The original blue graph is the top half of a parabola that opens to the right. The red graph is the right half of a parabola that opens upward. Together, these two graphs are symmetric with respect to what straight line? What is the straight line that cuts these two right down the middle? It's, oh, you really can't see it. Let's go with a darker green than that. I don't know if you can see that either. A little bit better. What's the equation of the straight line that cuts the first and third quadrants, both right down the middle?
Absolute.
Well, it's half of the absolute value, but over here it's a little different.
Oh.
It's y equals, well, there it is right there. Y equals x. Y equals x. It's the graph of the identity function. It's the graph of, sometimes this is called the do-nothing function. F of x equals x, f of 1 equals 1, f of 2 equals 2, f of 3 equals 3. It's the function that takes every number and does nothing at all with it, just leaves it alone. So if we take a function and its inverse, since the result of doing one and doing the other is the same as doing nothing at all, on average, evaluating a function and its inverse is like the do-nothing function. So that's the function that goes right down the middle of a one-to-one function and the graph of its inverse. They have symmetry about the line y equals x. Now there's several MyMathLab problems that give you a graph and then ask you what would the graph look like if you reflected it about the line y equals x. So a good thing to do is take a collection of points and just interchange their x and y coordinates and plot those points and connect the dots and see what that graph looks like. Okay, suppose we have a function like f of x equals 2x minus 6, and we don't know what the inverse of that function is. We don't know an algebraic expression that will undo those operations. There is a standard 4-step procedure for figuring out an algebraic expression that will define the inverse function. So I've got it there, and I've kind of spoiled it all, so I'll redo it from scratch here. So let's see if we can look at the 4-step process for finding the inverse of f of x equals 2x plus 6. 4 steps, I'll indicate the steps, and then let's go darker color than that so you can see it. I'll indicate the steps, and then actually carry it out with this linear function, f of x equals 2x plus 6. Step 1 is just notation. We eventually need to solve an equation, and it's easier to deal with the equation if it has x's and y's in it rather than f of x. So all we do in step 1 is replace the symbol f of x with the letter y. We know the function value is the y value, so pick up the y and pick up the f of x and put y in its place. So y equals 2x plus 6. It's just notation, that's all it is. So step 1, not much to that. Step 2, we actually do something. If we had a handful of ordered pairs, and that defined a one-to-one function, we could form the inverse function by taking them one by one and interchanging the x's and y's of all of its ordered pairs. Well, we have an equation. So what we can do, it's a lot more efficient, interchange the x and y variables. So in the equation, wherever we see a y, we put an x, and wherever we see an x, we put a y, and we've got it. Yes?
Now, would that work anywhere in the equation if it was like 2x plus, 2x squared plus 1x minus 6? So everywhere there was an x, you put a y.
Right. Everywhere there's an x, you put a y, and everywhere there's you put a y. Everywhere there's a y, you put an x. And, well, the hope is there's just one y when we're done with this because it's easier to solve for y, because that's the next step. But when we have it right here, this is actually an equation of the inverse function. And working just with the graphing calculator is great if you have y in terms of x. Graphing that in function mode is not as great. It can be done, but it's a pain to graph something if you have x in terms of y. But, I don't know, I've used GeoGebra sparingly in this class. I guess we use it a lot in the transformation section. But it has a nice feature where you can type in an equation, and I think I can actually type in the equation x in terms of y, and it'll give us the inverse. So if I type y equals 2x plus 6, there's that graph. Y equals 2x plus 6. And I think that's a fairly square viewing window. I hope so anyway. If I graph x equals 2y plus 6, having interchanged the x and the y, that should give us the graph of the inverse function, and the two should be symmetric to each other with respect to the line y equals x. So y equals x should kind of cut those right down the middle, and it goes up and to the right also, but also down here. So let's see if I could be a little bit more colorful. Leave the original function that color. Let's change this one maybe to, blue. And the one in the middle, we'll change that to green perhaps. That color maybe. Okay, so the original function, y equals 2x plus 6. The inverse function, x equals 2y plus 6. And the function about which they're supposed to have symmetry, the green one in the middle. Now, the thing that makes there more work for us to do, what we want to be able to do with this blue function, the inverse function, is we want to be able to take an x and have an expression we could plug that into and it tell us what the y is. We want to be able to take that 12 and plug it in for x and it give us 3. For the y value, but that's not an easy thing to do if we're looking at this, because if we put the 12 in for x, we have to solve an equation to figure out that y equals 3. So let's solve the equation now. Solve for y in terms of x. And if we do that, then we can use function notation and write this as the inverse function. So 2 or 3 steps to get where we need to go. I like to start off by interchanging the two sides. That doesn't always help, but usually it does, because we start off with x's on the right, and then when we interchange the x's and y's, we have y's on the right. But we want to end up with y's on the left. So if we interchange the two sides right here, kind of as a first step in solving this equation, it's a good step toward getting the y's on the left. So put the 2y plus 6 on the left and the x on the right. I'm not subtracting anything from both sides or anything from both sides, just interchanging the two sides. Now subtract 6. However it is, we're going to solve this thing for y. Divide both sides by 2. And it's linear, so maybe write it in something close to slope-intercept form, like y equals 1/2 x minus 3. X divided by 2. Is that equivalent to 1/2 times x? Divide something by 2, that's the same thing as taking half of it? Yeah. So 1/2 times x minus 3. Finally, step 4. It's notation, but it's important notation. Replace y by f inverse of x. F inverse of x notation, function notation. So we would write f inverse of x equals 1/2 x minus 3. So if I go back to the GeoGebra graph, and let's see, let's go with blue. This is my inverse function, f inverse of x equals 1/2 x minus 3. And if I take f inverse of 12, I want that to tell me, since the point 12, 3 is on the graph, I want it to be able to give me that y value of 3. So 1/2 of 12 minus 3, that's 6 minus 3, and that's 3. Okay, so we need to solve that for y in order for that to do what it needs to do there. That's not a bad graph. We'll see if we can salvage that. And maybe add to it.
Honesty, when you're working actual problem, then when you get to that 1/2 x minus 3, that's really not the end of it. You have to go back into a graph. Is that how you're going to want it?
No, that's just extra. Final answer in this particular problem that we just did is this. That is the final answer. F inverse of x equals 1/2 x minus 3. Okay. What if the function is more complicated? What if instead of just being a linear function, we've got a linear expression divided by a linear expression? Well, the graph is kind of on the rough side, and any analysis I did with this graph would be far more meaningful after we talk about rational functions. That's in the middle of chapter 3. Rational functions and vertical asymptotes, whatever those are, and horizontal asymptotes, whatever those are. So I won't say anything about the graph. But let's see if we can find, if we're just going to assume that it's a one-to-one function, because Mr. Mizell said so, and we're going to try to find an expression that will define the inverse function. That's the plan. So here goes. Let's find the inverse of this, what Mr. Mizell believes to be a one-to-one function. Step 1. Back to blue. Step 1, we want to replace the f of x with the letter y. So we have y equals 5x plus 3 over x minus 2. Easy step, no trouble with step 1. Step 2, also an easy step, but here we have more than one x. So there's just the one y, so put an x in place of that y. In both places where we see the x, we want to put the letter y. Put a y there, and put a y there. Step 3 is the hard step. Always the hardest step, because we have to solve for y. Now, I'm not going to take the time to interchange the two sides. That doesn't help out a whole lot. We want to deal with the fraction, and then we want to get all the terms that have y's in them on one side. So let's deal with the fraction. We've got a y minus 2 in the denominator. What can we do? Yeah, the LCD is our y minus 2, so let's multiply both sides by y minus 2. Y minus 2 over 1, if you like to think of it like that. We can then divide out those y minus 2's, and that will give us xy minus 2x equals 5y plus 3. Now, in the process of solving this equation right here for y, I like to take a breath and identify the terms that have y's in them. We're solving it for y, so we need to get some focus here. What terms have y's in them? Well, what's one term that has a y in it?
5y.
5y has a y in it. What's another term that has a y in it? xy. Are there any other terms that have y's in them? No. Okay, so these are the terms that have y's in them. I'd call them y terms, but the xy is technically an xy term, so it might hurt his feelings if I call it that. So these are terms that have y's in them. They have factors of y. These terms need to get together. They need to get together on the same side. So let's see if we can do that. Short of space, so I'm going to try to copy this. Get it? I need to learn Control C. That would save me some time. Control C, Control V. I always thought Control C was cut. Is that Control X? That's Control X. So Control C is copy. The terms that have y's in them need to get together on the left. So I'm going to subtract 5y from both sides. Minus 5y. Minus 5y. And while I'm at it, that minus 2x doesn't have any business being on the left with the terms that have y's in them, so add 2x to both sides. Plus 2x plus 2x. So xy minus 5y equals 2x plus 3. If that step goes well, the rest of it I'm thinking is probably going to go well. Common mistake is just to add 2x to both sides and divide both sides by y or by x and say y equals some expression that has a y in it. That just doesn't work so well. You need y on one side and no y's at all on the other. And I think we're almost there. Each term on the left now has a factor of y. So what can we do? Factor out that y. So write it y times x minus 5 equals 2x plus 3. How can we get y all by itself now? Divide both sides by x minus 5. Do I have room to do this? If I write real small, maybe. Divide the left-hand side by x minus 5. Divide the right-hand side by x minus 5. Those x minus 5s are going to divide out on the left. And I'm going to go ahead and put step 4 because I'm out of room otherwise. F inverse of x equals this expression. 2x plus 3 over x minus 5. Now let's see. I missed it. I was all set to try out my Control copy. Try again. Control C. Control V, and then back up there one more time. We grab this. There we go. Control C, Control V. So we have the function and we have the inverse of that function. Just want to test this out and see if the inverse function actually undoes what the original function f of x does. Does the inverse function undo what the original function does? So I pick a nice value of x and let f do something to that number. By nice, I mean if it could get by without involving a fraction, that would be great. So how about x equals 3? Would that be nice enough? Let's find f of 3. F of 3 equals what?
18.
Looks like 18. 15 plus 3 over 1. That's 18. So what f inverse is supposed to do is tell us where that 18 came from. So what should f inverse of 18 be?
3.
It should be 3. Let's see if it is. 2 times 18 plus 3 over 18 minus 5. That's 36 plus 3 over 13. That's 39 over 3. And that's 3. So what the function f does, or what the function f did to the number 3, the function f inverse undid. And it sent us right back to the original number 3. Now if we pick something other than 3, likely we're going to end up with a fraction, and complex fractions, trying to evaluate this, so I don't think I want to inflict that upon you. But this is what the inverse function does. It tells us where an original value, where we evaluate the original function f, came from. So how to finish that off? F inverse of f of 3 equals 3.